Alright guys, welcome to my Bachelor Thesis presentation. So today I would like to present my topic, and that is called Quantifying Predictive Uncertainty in Knowledge Graph Link Prediction. So let's start. So we will start with overview, then we will address the problem and how we approach them. And then at the end, we will try to summarize our results and we will draw our conclusion. So the name says Quantifying Predictive Uncertainty in Knowledge Graph Link Prediction. Quite a big name. But here, I would like to emphasize that we are focusing on one task, and that is link prediction. So, and specifically in knowledge graph. What is knowledge graph? So knowledge graph is a graph-based data representation where we represent each entities as nodes and their relations to another entity with links. And specifically the name says link prediction. So we are basically predicting links between nodes. And this task is quite used in a lot of different domains. For example, when you are predicting or when you are recommending something in e-commerce websites, or you are predicting connections between users inside social media network. All right. So that was link prediction. But how we do that? So there are a lot of different models into this, but specifically in my thesis, I have focused on graphical neural network architecture. And this is known as one of the best architecture in this task. And we use this specifically in autoencoder setting. So what is an autoencoder? So autoencoder consists of mainly two components. So the first component is called encoder, and the second component is called decoder. And in between, we have this latent space. So what is task of an encoder? So task of an encoder is nothing but summarizing all information it collects from the graph into one space where these information is represented as numbers, so-called as vectors and embeddings. All right. Once we got this embedding into our latent space, we use decoder to decode this information, which is understandable to us. We could do a lot of operations on that, more on that on the later part. All right. So in our architecture, we will start with RGCN model, and that is called Relational Graphical Convolutional Network. So it's an extension of RGCN model. It allows us to use multiple relations and it employs message passing as a framework. And on the decoder side, we will go with this mold. So now let's understand what these things are in detail. All right. So mainly, I would like to clarify that the underlying mechanism under these kind of models, under GNNs, is called message passing. So this is a framework which we use to understand the connections, to collect the connections between all of the edges inside the network. And how does it work? It consists of three parts. So the first part is called message collection, where we collect the embeddings of our neighborhood. So we know that who are in our neighbors, and then we aggregate them into one embedding. For in this case, we did summation of those embeddings. And the last step is called update. So here we update our own embedding with the collected message. And this helps us to understand who is our neighbor, and it is being done across the network. So all network knows who are their immediate neighbors and collect their informations. And we do it layer by layer in a model. So there can be 2 layers, 3 layers of message passing. So it's like one hop if it's 1 layer, 2 hop when it's 2 layer, and so on and so forth. Okay. So next, the middle part between encoder and decoder, the latent space. So this is the latent space. So once we get embedding out of those message passing layer, we, of course, map it into a space, right? Here we can perform operations on vectors to do downstream tasks. We do classification, clusters, graph classification, link prediction, and so on and so forth. And there can be different types of embedding models for arranging this latent space, because this is dependent on the models which we are using in decoder, because decoder will be a scoring function. But in this case, in our experiments, we use dismult. All right, so let's understand what is dismult. So dismult is type of scoring function where we use matrix multiplication. So how we do that? We take all three embeddings, so head, relation, and tail. This is how we call it. We call it as a triple, and we use it for our graphical neural network things. But how we calculate the scores? So we multiply each dimensions from each vectors together across all dimension. We do a summation of them. So this will give us a scalar value. And this scalar value, we pass it into a sigmoid function on later part to map the scores between 0 and 1. All right. So what are we doing? Like, why we are understanding this? What's the problem, right? All right. So the problem with the RGCN network is that it is too underconfident. And that means on the right hand side, you can see it's a reliability graph. So reliability graph tells us if our model is good calibrated, bad calibrated, perfectly calibrated. So if the model's predicted probability aligns with the future or with the accurate or the real life probability, then it's called perfectly aligned. So the dotted line here on the right hand side symbolizes perfectly calibrated model. And the line with the dots is the model itself, the calibrated line. All right. So if the dotted line, if the model's line is above the dotted line, that means model is underconfident. And that being said, model doubts itself more than it should do that. So for example, simple example, if our model says that 20% chance that this links exist or this customer is a fraud, but in reality, that customers can be more than 20% chance. So it can be in reliability, if you test it 100 times, that customer will be fraud more than 40%. So this gap of 20 minus 40, that is 20%. And that is basically unreliable in production environment. And this is how we could lose a lot of things in a lot of the critical domain like healthcare and financial domain. So we cannot use it. We need to calibrate the model. And for that, we will try to achieve those calibration in next steps. So that was the problem. How we do that? So we will try 3 different methods. We took the inspiration from deep learning. So we'll start with regularization, and then we will do estimation. So estimation is when you estimate uncertainty. And the third is post-thought calibration. So this is more like you don't have to like train it again. It's more like a post-source things. After training, you could calibrate your model with perfect calibration. All right. So let's start with approach. What approach we will take? So we start with two data set, and these 2 data sets are benchmark data set. So these data sets are being used in literature for the task of link prediction, evaluation of the model, evaluation of the techniques and architectures. So when we take this data set, we are sure that these data sets are reliable and quietly balanced. All right. Then we do model training. So we'll train our model, fine tune it, and so on and so forth. Then we'll try to use uncertainty handling method. So we'll try to incorporate those methods into our architecture, in our task, in our pipelines. And the last thing is evaluation. So in evaluation, we will mainly evaluate into 2 dimensions. So the first dimension is performance, and the second dimension is uncertainty. So in performance, we will use MRR, mean rank, and hit site K. So hit set k will be 1, 3, and 10. But these metrics are widely used for link prediction task. So we choose them. And the uncertainty quantification task, we will go with expected calibration error, barrier score, and reliability graph. These three are different metrics to understand and to visualize and also to quantify how bad calibrated model is. So EC score is based on a binning method where you make bins of the calibration range and then you take the average of the model's confidence and the correctness in that bin. And the barrier score is more like R2 square error. So you take the differences and square them and sum it up to form a quantity. All right, now let's understand the pipeline, what pipeline we will be using. So here we will start with initializing our features with one hot encoding. Then we will follow the two-layer RGC and message forward pass, where we will use two-layer RGC model. That means we will use 2 layers of message passing. And of course, the methods like basis decomposes is add-on. So these are like regularization within the network, within the model itself. It is not added, this is part of the model. All right, we will also try to use batch norm, dropout layers, and so on and so forth, because this helps us in general in neural network. All right, and then we will form this final embedding, entity embeddings. And once we got this entity embeddings, we now have the information of the graph. But how do we backpropagate? So we do negative sampling. So this is a technique where we either corrupt the head of the triple or the tail of the triple. So these are negatively formed links. And then once we have this positively formed links, which is nothing but the graph itself or the data set itself, and this negatively formed links, we have 2 methods, and then we train a binary classification using decimal decoder. So that being said, we use a scoring function of this, and here we maintain relation embedding suite. So our relation embeddings are also maintained in decoder. All right, and then we will train it according to the base binary cross entropy loss. Okay, and then when we are backpropagating, we will update the weights and initial embeddings related to the loss. All right, so now let's start with the fun part. Let's start with applying those techniques, where we will apply these regularization techniques and which techniques we will use. So the first technique which we use is called edge dropout. And what is edge dropout? So edge dropout is dropping a few edges before passing our graph into a message passing layer. So we drop out few edges, we keep them out, and we pass the rest of the graph into message passing, and then we use the dropped edges or the full graph for the negative sampling. That means the loss will be calculated over the full graph, but the message passing was only done on the sum part of the graph. So this helps the model to understand more robustly the dataset and generalize way better than it normally does. So this is the first technique. So second technique will be label smoothing, where first, so here we are using zeros and ones. These are hard labels. We will replace them with the soft labels. So instead of 1 and zeros, we will use 0.95 and 0.05. So these are softer labels. And these helps our model not to converge or train its weight such that we only produce zeros and ones. When we do this, it tells model that, hey, you can also produce values which are between zeros and ones, not extremes. Okay, so these two are regularization methods. So the second technique we discussed was estimation. So into this technique, we have 2 choices. So the first technique is called deep assemble. What does deep assemble mean? That means we will train 3 different models Same architecture, same data set, same pipeline. But the initial points or initialization of these three different models will be different. So once we train these three different models together into three different loss functions, three different pipelines, they will end up at three different minimums. And that being said, these three models will have different opinions and different combinations of it. So we will produce a diverse suite of models. And this suite will help us to estimate the uncertainty of the input triples or the samples. So higher the variance, higher the uncertainty is about the data set. And better the diversity, more better our responses will be. All right, the second technique was called Monte Carlo dropout. So this is similar technique to disassemble, but instead of training three different models, we train only one model and we use dropout as a differentiating factor. So what is dropout? So dropout is not similar to edge dropout, but this is for weights. That means we drop out some weights during inference and we take the model's confidence scores. And we do it for three different times for this example. That being said, we will have three different values or three different opinion of the same model, but three different Bayesian value out of a distribution. That says that we will have the same model, but three different opinions, and then we again achieve the same thing, different diverse responses. And of course, we could use in a similar way, like taking mean and variance. All right, so these were the two estimation techniques. Now let's try to understand the third technique, which was post-thought calibration. Here we will start with temperature scaling. So what is temperature scaling? It is nothing but a scaling technique. So when you have your model underconfident and you want it to be slightly confident, what you do, you just divide it by a number which is lesser than 1. That will scale the values to an higher values because it will increase the value. Exactly, that's the only concept about scaling. The Platt scaling is a extension of temperature scaling. That means that we will also scale the distribution, but we will also localize it. That means we will also shift it. So we could also scale it and we could also shift it. So this gives us more flexibility. And the third method is isotonic regression. So here we don't use any parameter. Here we are finding a step function which is non-decreasing and which reduces the R2 square error. That means we could perfectly do a regression on the distribution and directly fit our model's calibration with those regression. And this helps us to calibrate our model. All right, a lot of talking. Show me the results, right? Okay, so let's start with results. So we will start with the baseline result. That means we will start with vanilla model. So no edge dropout, no label smoothing, nothing. Direct the model out of direct the factory. All right, so let's check the performance. So here the performance was evaluated at, so we will take MRR as a main indicator for the performance. And here we can see that our model is better off in one data set as compared to the other. And FB15K 237 has performance of 22%, and WordNet 18RR has performance of 39%. So our model is way better, and we train it with early stopping, of course. Now let's evaluate on second dimension, which is calibration. Here you can see the red part. So red part says how much gap we have between perfect and the model. And the barrier score of around 30 is way high. We can exactly prove here that using our vanilla model wouldn't help. This cannot be used in production. This model needs to be calibrated. Otherwise, it could create problems. All right, so we have to calibrate, and in next few methods, we will try to calibrate it. All right, so let's move to regularization and its impact. So let's try to understand how it impacted the performance, which is our first dimension. Remember. All right, so we will start with edge dropout, and we saw that there is an increase in the performance of FB15K 237. That means one of the data set, both of them increase, but FB15K 237 has higher impact. So edge dropout was successful because it increases the performance for both of the data set. Now let's try to understand how label smoothing performed. Again, it also increases the performance of the dataset. That means that we have a hit here. But in the label smoothing, one important part is that it increases and it performs well for one of the dataset as compared to other. That means we will have this choice. What choice we have? Either we use edge dropout or we use LS, which is label smoothing. But we also have third choice, which is combining them together. What if it performs better? Exactly, that's what we did, and we saw it did. So WordNet 18R performed better when we used this combination. So performance was boosted by this, and we achieved 50% of hits at 10, which is way good for this dataset. But for the other dataset, we saw that combination didn't help that much, as it was better when we only use edge dropout. So again, we have a dilemma, like which one to go with, combination or edge dropout. We go with greedy approach. So greedy approach says we select the best thing at every step. So at this step, we achieve the best results or best performance for FB15K 237 was the model when we used edge dropout alone. And for other dataset, we combine them. So we will use these two models for rest of the experiments, right? All right, now let's check the calibration or their effects on calibration, because we want calibrated model as well as good model with good performance. All right, so on the right hand side, you can see the graphs where each bar explains you or shows you the performance of calibration. Here we are measuring ECE scores and barrier scores. That means lower the score is, better the calibration is. And we saw the best effect was shown when these two models are applied together. That means that we could use this combination if we are targeting calibration over performance. But I have a better way than this. So now, right now we choose the model which is performing better over the calibration, and then we try to calibrate those models, because then we could also minimize the calibration error and maximize the performance. All right, so we go with only edge dropout for FB15K 237 and the combination of these two methods for WN18RR. All right, that being said, now let's move to uncertainty estimation. So here, these two graphs shows us the performance of uncertainty estimation method. So we saw quite an increase in performance for deep assembled model. So it's quite a success. Here 10 to 12% or 15% in some cases of boost in performance is way better for these two data sets. But for the Monte Carlo dropout, we see a decrease, a slight decrease, because it's a probabilistic thing. And we see slight decrease in performance. That means if we have a choice between these two, we would choose deep assemble because it increases the performance. Okay, let's see the effects on calibration, which is our second dimension. Okay, when we see the effect of these models on calibration, we could see that there is no such reduction in EC scores. That means these methods are not helping in calibration effects. Okay, but we understood that variance will be the factor which we will use for estimating the uncertainty. And exactly what we did. So we tested our model on the positive triples and the corrupted triples. And we tested the variance, like we averaged their variance and saw exactly what we assumed. We saw higher variance for the model which were corrupted, for the triples which are corrupted, and lower variance for the triples which are positives, which are nothing but a normal triples. So this was a win because now we can put human in the loop when there is a higher uncertainty to check if the model is right or if the model is explainable. Right, but except one case. Here in Monte Carlo dropout, we saw lesser variance in corrupted as compared to the positive. That says that the problem here is nothing but we could not use a Monte Carlo dropout in production because sometimes it may produce lesser variance for some of the corrupted triples or some of the false positives. So it can create false positives and we will not check them because their variance is low. So it's a problem to use it in production. Okay. Now let's try to use post hoc calibration methods. Like temperature scaling, we'll start with temperature scaling. So here we can see there is a reduction in EC scores. So it's a good sign. And it didn't decreases the performance. So it's also a second good sign. But the issue is these scores are still higher. These errors are still higher. The model is still uncalibrated. That means we cannot use this technique. Now let's try to understand the performance of Platt scaling. Okay, when we tested the Platt scaling, it reduces the MRR by 2 to 4%. But the major chunk of reduction was in calibration error. That means this method calibrated our model because now our errors is near 3%, which is quite good. We could use this in production. All right. Then the third method was isotonic regression. This one was by far the best, 2,200% in reduction in calibration error, which is great. But the problem here with the third method is that it decreases the performance of the model. So on the two-dimensional scale, Platt scaling is the only method which balances both dimensions. So it reduces the EC scores, the calibration errors, while maintaining the performance of the model. That means we could use Platt scaling. All right. So if we can calibrate MC dropout and deep assemble, we could create a model which is higher performant and good calibrated. So in this graph, we could see 4 different combinations. Here the red curves explain us temperature scaling. The green curve explains us the isotonic, and the blue curve shows us the Platt scaling. Here we can see that Platt scaling and isotonics are comparable. They have similar ECE scores and they calibrate our model perfectly well to a perfect calibration. So we could use that, right? So now the question is which method to use and how these methods perform is computationally expensive. So the training cost of deep assembled model is M times more than a single model. because here we are using 5 models and for the same task. So training time will be higher because we are training 5 models. But the inference cost can be optimized similar to one model with MC dropout. So these two, like for example, deep assemble and MC dropout have similar inference cost, right? All right. So after discussing all these methods, what is the best combination? What is the conclusion? So we start with regularization. We check which regularization methods are better. So if we are optimizing the calibration, we go with the combination. Else, if we are optimizing performance, we will go with the edge dropout for the models which are suited for them. All right. Then we will apply deep assemble because it increases the performance. If you are allowed to use higher computational or you have higher computational budget, you could use deep assemble because it gives you more accuracy. And the third method which we will apply is we end up scaling our model with plot scaling because it will perfectly align or calibrate your model, and you could use it in real inference in real production environment, and you can trust it generates reliable results. All right, so now we have the combination, but a little side quest which we have seen or which I have done in my study is more on effect of relation types. So what if all of this uncertainty is nothing but an epistemic uncertainty? So epistemic uncertainty is an uncertainty which is arising due to the model's complexity. If the model is less complex than what it needs to be, or we have to use more data to train it. So then the model will be less complex, more trained, and then we could basically use it, like more data will solve it. If we can prove that our model is if this uncertainty is arising through epistemic uncertainty, we could try to solve it using some techniques. All right, for that, what we did is we separated the relations and tested our model on that. So we used symmetricity and asymmetricity as a separable parameter. So we use, for example, we separated the 11 relation of WordNet into symmetric and asymmetric, and then we tested our model only on symmetric relations and asymmetric relations, and we saw that there is a higher increase in the barriers in the performance of the model, and the model is well calibrated on these sets, on these relation types. So that indicates that our model is better in symmetric as compared to asymmetric. And this might be arising from our Dismult decoder, because Dismult is known to be higher or better for symmetric relation as compared to asymmetric relation. So in future study, we could test different embedding models. So once we tested like trans E or complex E, then we can directly compare those results on the relation types with Dismult results. And then we could basically pinpoint which areas is giving this arise to these uncertainty. And the second study we could perform is systematic removal of the relations by their types from the data set, and then training and testing. So we could start with one type and then we remove it, training and testing, then again, and we measure the uncertainty and performance. So once we have these systematic study of the data set characteristic, we could basically measure what is creating this uncertainty. If it's data, if it's complexity of the model, which is lesser, we could basically quantify and we could solve this problem of uncertainty. and we could generate a model which is perfectly calibrated instantly, so we don't need any calibration afterwards. And this how we could also solve the problem of bad performance. We could also increase performance because now we have indication where our model is weak, and we can focus more on that part and improve our model. So that being said, this was my time. Thank you so much for listening, and please write a comment if you have any questions. I would happy to give you more information. Thank you for listening, and see you guys.